In this video, I'd like to talk about multiplying and dividing rational expressions. And so in these example problems, we're going to have two different rational expressions, and we're either going to multiply them, like in this case, or we will divide them. So before we jump into this specific problem, let's try and come up with a strategy for how to deal with these problems. And one helpful reminder is to think about how normal fractions would multiply together. And remember, if you have something like 2/3 multiplied by 4/5, let's say, that when multiplying fractions, you really just go straight across in the numerator and the denominator. And you do 2 times 4 up top and 3 times 5 down below. And so in this case, you get 8/15. Whereas if we are dividing fractions, we'll just use those same numbers, then remember that division is the opposite of multiplication. So if we're dividing by a fraction, it's the same thing as multiplying by that fraction flipped over. And then once you get to multiplication, then you just go straight across again, and we get 10 up top and 12 down below, which simplifies to 5/6. So that's the general process that with these problems in multiplication, we can just multiply straight across. So this top times this numerator and this denominator times this denominator, and then we can try and simplify. But when dealing with rational expressions, often you can make simplifications as you go. And one of the strategies we'll employ here is that many of these expressions are going to be factorable. And often when you factor these expressions, you can make some nice simplifications. So we're going to start these problems by factoring and then just employ normal multiplication techniques. So let's start this problem by first clearing out a room and just rewriting this. And now that we've rewritten this, the first thing we want to notice is that for each of these, they all can be factored, though we'll have to use different techniques. For instance, for each of these numerators, we can factor by pulling out the greatest common factor. So for this expression here, notice you can factor out a 5 from each of these terms. They're both divisible by 5, and we'd be left with an x minus 2. And if you're unsure with your factoring, remember you can always just redistribute and prove to yourself that it would be 5x minus 10, which is what you started with. And in this denominator, notice we have a difference of 2 squares. If you have 2 squared numbers and you're subtracting, this factors into a minus b times by a plus b. It's always the first one minus the second one, ignoring the squares, times by the first one plus the second one. And x squared minus 36, 36, remember, is really just 6 squared. So we can factor that as x, the first one, minus the second one, ignoring the squares, multiplied by the first one plus the second one. So that's our first rational expression. Now we'll look at this one. And for this one, notice that for this expression, we can pull out the greatest common factor. They each have a common factor of 4. In fact, I would recommend always start by looking for the greatest common factor. Now, on the bottom ones, you can't do that since you have terms without x in it, and they don't have any common factors that you can pull out. But it is always helpful to start with that because that will often simplify your work. So we can pull a 4 out from these. We can factor that out. We're left with an x plus 6 there, since 24 divided by 4 is 6. And for this denominator, this is a normal quadratic, which can be factored into 2 different binomials. And we know each of these will have 2 terms. And the first terms will have to be x and x, since the coefficient on x squared is a 1. Now, if it was not a 1, then you would have to use grouping, and that may or may not work. Sometimes, in fact, most of the time, quadratics are not factorable. But in these example problems, and most likely if you're in a class learning this, your teacher is going to craft the problems often so that they are factorable. So it is worth checking, since a lot of times these do actually factor, just because the problems are crafted that way. But if you found some random quadratic with even decimal or just slightly changed numbers, in all likelihood, it actually doesn't factor, not easily at least. So this one does factor though, and we know the first terms are x and x since that's what makes x squared. And at this point, we just need to find these two number terms since we know they multiply to -14 and they're going to add to 5. So let's look at the factor pairs for -14. Could be -1 and 14, 1 and -14. Could be 2 and -7 or -2 and 7. And like I mentioned, we also know they're going to add to 5. So that has to be -2 and +7. So let's make some room for ourselves and copy and paste what we have so that we can try and make some cancellations. So one thing to notice is that we have an x minus 2 up top and down below. Now remember, at this point, since we factored everything, we would just multiply straight across. So in reality, we can just put all of this in one fraction. So let me write that really quickly. And essentially, everything in the numerator is all multiplied together, and everything in our denominator is all multiplied together. Now, once you get enough practice, you don't need to rewrite this again, but I just want it to be explicitly clear that we are now essentially combining this in one fraction because multiplication, you can just multiply the numerator of the first fraction by the numerator of the second fraction, and the same thing for your denominator. Now, multiplication is also able to be rewritten in any order. Like we could move the 4 out in front and do 5 times 4 and make that 20, which we will do at the end. We know 20 will be in our numerator, but we can also make some cancellations. Since notice, we have an x minus 2 up top and down below. So something divided by itself, that's just 1. So they will cancel out. And we have an x plus 6 up top and down below, so they will cancel out as well. And that's all the cancellations we can make. So up top, we're just going to have this 20. Actually, let me just move it to the center. So we have 20 up top. And down below, we're left with that x minus 6 times by x plus 7. So this is our fully simplified expression, and if you want, you can even expand that denominator, but you don't have to. And at this point, we just need to figure out which x values we need to exclude from our domain here. And that's this second part. And what I would recommend doing is looking at the expression before we made cancellations. So we can actually just look at this right here, the white piece, and figure out which x values we cannot plug in. So let me just make a bit of room. And we can say that x cannot equal, well, 6, since if you put in a 6 here, you get 6 minus 6, which is 0. And it doesn't matter what the other terms are when you plug in 6, because 0 times anything is 0. So 6 cannot be included, as well as -6 there. And over here, if you plug in a 2, this will become 0 times by everything else, which again is just 0. And right here, -7 cannot be plugged in. So 6, -6, 2, and -7, all of these terms are not in the domain of these expressions multiplied together. Since in any case, when you plug these in, your denominator would become 0 in one or the other rational expression. So with that in mind, let's look at two problems where we're looking at error analysis. We're going to look at someone else's work and try to find the mistakes. And then in the following video, we'll look at two more problems that we have to do all the work ourselves.